Math 242, I'm Joe Vasta. This is section 6.1, and the section is called Exponential and Logarithmic Functions. So an exponential function is a function where the variable is in the exponent, like these two functions here. Let's go ahead and graph the first one by plotting some points. Well, if x is 0, 2 to the 0 is 1. If x is 1, 2 to the 1 power is 2. X is 2, 2 to the 2 is 4. So let's graph some of those points. 0, 1, 1, 2, 2, 4, and you could put 3, 8. You see your graph is going to go up like that. Now let's plot some more points, like a -1. Well, y equals 2 to the -1. That's really over 1. You cross the line, change the sign, and that's 1/2. And by the same reasoning, you can plot 2 in for -x. It's 2 to the -2, which is 1/4. And so, this exponential graph looks like this. It looks like a plane taken off. Okay? But actually, if you go this way, the graph will never touch the x-axis. The x-axis, we've seen this word before, is a horizontal asymptote. Okay, if you put 3 in instead of 2, we'd actually get the same picture, except it would be rising faster. And if we put 5 in instead of 2, it would be rising up even faster. Okay, well, what happens if you put 1/2 in as the base? Well, let's go ahead and plug some numbers in like we did before. This time I'll go -2, -1, 0, 1, 2. If x is 0, we have 1. If x is 1, we have 1/2. If x is 2, we have 1/2 squared, which is 1/4. If x is -1, we have 1/2 to the -1. And so this is like 1 to the -1 over 2 to the -1. And cross the line, change the sign. You end up getting 2 on the top and 1 on the bottom. That's a weird 2. So I end up getting 2 here. And if you put 1/2 to the -2 power, that's actually going to give you 4. So let's plot some of those points and see what happens here. We have 0, 1. 1, 1/2, 2, 1/4, -1, 2, and -2. I better label these here. -2, 4. So it actually looks like this. It gets closer to the x-axis as you go to the right. The x-axis, again, is a horizontal asymptote. that horizontal asymptote has the equation y equals 0. Y equals 0 on that one as well. And so when you have a number like 1/2 in there, it's the plane landing. But it actually never touches the runway. It just keeps getting closer and closer to the x-axis without touching it. It's hard for us to imagine that, but that's what happens. And so this graph right here is really a reflection of that graph. And we can do something with transformations on this, but we want to move on. So you have exponential graphs, exponential functions. They are functions. They pass the vertical line test. They are one-to-one functions. They pass the horizontal line test as well. They will always look like one of these two creatures. And when will it look like the plane taken off? When that base is greater than 1. When is it the plane landing? When the base is between 0 and 1. If the base is 1, you just end up getting 1 to the x, which is y equals 1. So we don't have the base equaling 1 or negative numbers. Let's go ahead and summarize what we've done on this piece of paper right here. I'm going to go check, see how things are coming out on the camera. It's good enough for government work. So what do we have here? Everything that I said. Anytime you have b to the x, which is an exponential graph, you'll always have y equals 0 as the horizontal asymptote. That's the x-axis. You'll always have a y-intercept, 0, 1. And you'll always have the point 1, comma, b. And to show you that, in these examples, b here was 2. You have the point 1, 2. And here, b is 1/2. You'll have the point 1, 1/2. So let's take a look at this. This looks just like the other two graphs I did. And your exponential graphs, we just want to say they will always look like this. Here's the plane taken off, and here's the plane landing, but it never touches the runway. So what are they going to have you do in your homework? Well, in 58 through 63, I think, they're going to have you do graphs that look like that. So they're having you do transformations of the exponential function. So the first thing we want to do is identify what is the mother graph. Well, the mother graph, f of x, hopefully this is thick enough, it is 2 to the x. 2 to the x, we want to remember a few things about it. It has a y-intercept of 1. It has another point of 1, 2. And it has this runway here, which is y equals 0. This is y equals 0. Now, you could, if you want, graph the plane taken off. But I'm kind of concerned with the transformation here. So this is a transformation of graph f. Let's go ahead and write out the transformation. Some of you might already know what happens to the graph. I'm going to rewrite this, and this is what a lot of people don't like in class, is when you go f of x minus 2 minus 3, and everybody says, where did the 2, this big 2, go? Well, it's built in here, because if you put x minus 2 in here, you get 2 raised to the x minus 2, and we're subtracting 3. In any case, we see that our mother graph moves 2 to the right and 3 down. 2 to the right, let's make our intermediate points be in red. I'm going to move everything 2 to the right. So I end up getting 1, 2 with that point. 1, 2 with this point. We also have to keep track of the wall. The horizontal wall is going to move 2 to the right, and if you move that 2 to the right, you end up getting the same thing. My final graph, we'll make it in black ink, 3 down. So I take these 2 dots here and move them 3 down. 1, 2, 3. 1, 2, 3. And the wall is actually going to move this time. The horizontal asymptote will now move 3 down. 1, 2, 3. So I put a dashed line here. And we end up getting something that looks like this. And so the original graph, we didn't actually draw the whole thing out in blue with the plane taken off, and we have a similar graph for problem number 1. Problem number 2 is g of x equals e to the negative x plus 1. Well, first of all, we see this e here, and it might be kind of new to us. E is actually equal to 2.718281828. I sound like a computer here. 18281828. But then it actually changes to 4, 5, 9, and kind of continues in sort of a random fashion, but it's not really random. It is the number e, and it is an irrational number. Cannot be written as a fraction. Can be approximated maybe with a fraction, but not written exactly as a fraction. This number is between 2 and 3. So the mother graph, which we'll make in blue, f of x equals e to the x. Now, I know this is a little new for a lot of you, this number e here, but if you want, you can pause the video and try to see if you can graph g of x on your own using transformations. Okay. I'm going to go ahead and write this graph, e to the negative x plus 1. I'm going to write it in terms of f of x. This is really f of negative x plus 1. And all I did is rewrite it in terms of that function. I plugged negative x in there, it's e to the negative x, and we have plus 1. So what does this do to the graph? We're following our CBAD order. This reflects through. Now this is the one we want to remember. We want to remember our reflections. It reflects through the y-axis, and then it moves 1 up, or up 1. So let's make our original graph be in blue. It always has the y-intercept of 1. I know that's hard to see that that's blue. And it has the point 1, comma e, or 1, comma 2.7. So I'll just make it in between. It almost looks like 2.5, but that's good enough. And then it always, these graphs always have the runway there on the x-axis. My intermediate graph, I'm going to reflect those 2 points through the y-axis. Well, when I reflect the one that's on the y-axis through the y-axis, I end up getting that point again, which so it's hard to see that that's red. And I'm going to go ahead and reflect this through the y-axis. I end up getting this point right here. So now, if the wall gets reflected through the y-axis, it stays where it is. So now what I have is I end up having, if I had to draw the red graph without the plus 1, I'd have the airplane landing. Okay, because we'd have this red dot, and I know that that's a red dot there, even though it looks pretty dark. Now what I'm going to do is I'm going to move those two dots up 1. The final graph will be in black. And what else moves up 1 is the wall. So my final dots are right here in the wall. So let's see if we can make this graph look nice. And there is our final result. So you'll have more of those in the homework. So now we are going to do something where we're solving exponential equations. Your homework, by the way, better put this on the front page. Front page. If I can find the front page. Your homework includes a handout and bookwork. So that's the homework. We're going to do stuff that will help you with the handouts. And the handout is solving exponential functions. So when we're solving exponential functions, we're not used to solving functions with the variable is up in the exponent. But what we're going to do here is we're going to get a common base. Is there a common base between 3 and 81? Well, the answer on this first one is yes. The common base is going to be 3. So like 3 to what power gives you 81? And you can think about that. 81 is 9 times 9. And then there's 3, 3, 3, 3. So it's going to be 3 to the 4th. So with exponential graphs, or exponential equations, once you have 3 to something equals 3 to something else, you can set those exponents equally to each other. And we can do this because the exponential function is 1 to 1. We won't get into the details of that right now. So I'm going to solve this equation. Negative x equals, subtract 1 on both sides, 3. X equals negative 3. And there's the answer. So now we're going to try this one here. We'll ask the question, is there a common base you can get between 27 and 81? You might want to pause and see if you can do this one on your own. Okay. The common base is 3. 27 is 3 cubed. 3 times 3 is 9 times 3 is 27. Then I write to the x power. 81, we already solved from the last problem, is 3 to the 4th. So I have a power to a power, which means I multiply 3 to the 3x equals, I'm going to cross the line and change the sign. This is one of those times when we want to make the exponent negative because you want everything on the same line. 3 to the negative 4. I have common base there. 3 to this equals 3 to that. So I set this equal to that. And I divide by 3 and get my answer of negative 4/3. Okay, we'll continue. So see if you can do problem number 3 on your own. What is a common base we can get here? Well, there's a few answers. One answer, probably the easiest one, is 8 is the common base. But you can argue 2 is the common base. That's another common base you can get, and the problem will work out to give you the same answer. 64 is 8 squared. So I have 8 to this equals 8 to that. So I'm going to take the this and set it equal to that. So I add 2 to both sides, and I divide by 3 on both sides. So x equals 4/3. The answer is not always going to be 4/3 or 4/3, negative 4/3. It's just the way it worked out this time. So that is how you do these problems. You might not want to pause the video and do this problem. I put this up here because it's hard to think of a common base. There is no common, we cannot find a common base. It would happen to be an irrational number, but we're not going to talk about this. So when you can't find a common base, this is called type 2. Type 2 exponential equations. And we cannot do this yet. So I don't want you to get the wrong idea and think that you can put that on every test problem. The other ones that we did, 1 through 3, those were type 1 exponential equations. Okay, well, this frustrated people throughout the years, and in the 1600s, someone named Napier came along, and he said, well, there is actually a number, a real number that would make this work. 7 to the x equals 12 does have a number that makes it work. That number is between 1 and 2, because 7 to the 1 is 7, and 7 to the 2 is 49. So there is a number between 1 and 2 that would make that work. So Napier came along and he said, I'm going to define something. So this is a definition. Well, x is a real number that exists. I'm going to define something called a logarithm. And we put the word log. We write the base right there in the basement. And we put this right there. There's the 12. And that is what a logarithm is. So all logarithms are exponents. Let's go ahead and look at the definition of a logarithm. This is the definition. A logarithm is that exponent c. c equals log base b of a. And it is just a definition. This is called the exponential form of the equation. This is called the logarithmic form of the equation. The exponential form sometimes I'll call Clark Kent, and the logarithmic form I'll call Superman. The reason I do that is because these guys are the same person. This is just looks a little differently. It's dressed up a little different. How would we say this? C equals log base B of A. And so they're going to ask you in your homework to go from Clark Kent to Superman, and they're going to also ask you to go from Superman back to Clark Kent. And so that is what we'll do. Let's see if we can do these kinds of problems. Rewrite in the other form, meaning if it's Clark Kent, turn it to Superman, and if it's Superman, turn it to Clark Kent. I'm actually going to fold this piece of paper here. And so it says, rewrite in the other form. Whenever I change forms in lecture, I'll put an arrow to indicate that I'm doing this. So what logarithms are the exponents. I know the b to the c is on the other side. I always start off by writing the exponent, which is 5. 5 equals log base b. Okay, so what's the base there? The base there is 2. And it's written as a subscript. And the other number that we put here is 32. Now your book will always put parentheses right there. So I didn't put them right here. Another thing to remember, because we might as well get this straight, that number there is called the base, This number here is called the exponent. And this number here, lots of times we like to call this the argument. And that we can say the same thing up there. We can point A, B, and C are called the same thing up there. So we are done with this problem here. We have managed to change Clark Kent into Superman. Okay, let's go ahead and do some more problems. We are going to change log. Oh, this problem is not written all the way. I'm going to set this thing equal to, let's just say, W. So this equation is in the log form. I guess I should have put this back here. So it's Superman, and we want to change it back to Clark Kent. So the way I begin doing something like this is I start off with who's in the basement. What's the base? The base is 8. The exponent is going to be, it's not what you think. You know, like if you're first seeing this, this almost looks like this guy's exponent. That's not going to be the case. The exponent is W, and this is going to equal the argument. And so that's how you do these problems. Now here's the deal. Some teachers would say, hey, this is what you should do. You should look at this and then say, hey, this is C, and this right here is B, and this is A in the parentheses, and you should use this definition and write out B to the C equals A. And that's all right. There's nothing wrong with doing that. Let's continue now. Now this definition here, if you don't get this, the rest of chapter 6 will be a complete nightmare for you. Okay, so problem number 3 says log 100 equals 2. Now there seems to be something wrong with this problem, or something missing, and it's the fact that there is no base written there. When there's no base written there, this logarithm has a name, and it has a base. When there's not a base written there, it is base 10, which is called the common logarithm. I'll just say common log. And so when you get that, it really says log base 10 of 100 equals 2. I'm going to go ahead and change this from Superman back to Clark Kent. So the base happens to be 10. The exponent is 2. And the argument is 100. So there's the answer. All they want you to do is do this. They don't want you to go 10 squared. It is 100. And there's our answer. We're just doing this conversion. The last problem has some more notation here. ln, which is really base e, which is sometimes called the natural logarithm. And that's used a lot. When you see an ln, you can write log base e of the argument equals 1/2. Okay, so now we're ready to change this from Superman back to Clark Kent. The base is e. The argument, the exponent is 1/2, and the argument is the square root of e. And so we have finished the problem. All they want you to do when they're asking you to rewrite in the other form is to get this definition down of what a logarithm is. These 4 problems will help you with 1 through 15 on your homework. The next few problems that we do, they'll ask you to evaluate logarithms. Now what does that mean? Well, this is going to give me some answer. Log base 2 of 64. So I'll go ahead and do these problems with a different color. I'll use blue. Hopefully the colors are showing up. I don't know what this is, so I'm going to set it equal to x. Now I'm going to change this from Superman back to Clark Kent. What is the base? Who's in the basement? 2. And the exponent is x. The argument is 64. So now what we have is a type 1 exponential equation. What's the common base? Looks like it is 2. So let's see, 64 is 8 times 8, and each 8 is 2 times 2 times 2, so this is 2 to the 6th. And now look what I have here. 2 to this equals 2 to that. So I'm going to say that this equals that. X is 6. Now x was never part of the original problem, so our final answer is just going to be 6. So there it is. Let's go ahead and try this next one. So maybe you can pause the video and try it. I'm going to wait, or I'm not going to wait. Pause the video and then unpause it. We set this equal to x. Okay, now what I'm going to do is I'm going to change this from Superman to Clark Kent. I'm going to write this as the base and the exponent. So I'm using that definition of logarithms. This equals the argument. And our question is, can we get a common base? And the answer to that question is yes, the common base is 3. This is 3 to the x equals 3 to the 1. We have 3 to this equals 3 to that. We set this equals to that, and we end up getting x equals 1. So we have just evaluated this logarithm. Log base 3 of 3 equals 1. Let's consider if we had a 5 there and a 5 there. Well, the same thing would happen, and you would end up getting a 1 there. And if you had a 7 there and a 7 there, the same thing would happen, and you would get a 1. So there is a property of logs that says log base b of b equals 1. Now, it's not a property, that you have to memorize, because you could always reinvent the wheel on that by doing what we did here. Also, before we move off this page, another thing to note is that once you get better at this, you don't always have to do the problems this way. You can just in your mind say 2 to what power gives me 64 to the 6th. And over here, 3 to what power gives me 3 to the 1. But there are some that are going to be a little more difficult than that. So this is why I'm showing you this way with the type 1 exponential equations. Problem number 3. So go ahead and try problem number 3 on your own and see what you get. Okay, we set this equal to x. There's the Superman, the logarithmic form, and I'm going to go ahead and change this to Clark Kent, which I look for the base, which is 49. It's going to hold up the exponent, which is x. This equals 7. I want to get a common base. The common base would be 7. So 49 is 7 squared. And then this is 7 to the 1. I have a power to a power. I multiply. And I have 7 to this equals 7 to that. I'm going to take my this and set it equal to that and solve that equation. X equals 1/2. So my final answer is log base 49 of 7 is 1/2. There was no x in the original problem, so my answer is just 1/2. And really what it means is 49 to the 1/2 power gives me 7. And anything to the 1/2 power is the square root. Square root of 49 is 7. Okay, so here is problem number 4. Maybe you want to try this on your own. Hit pause and come back. Here we are. I'm going to set this equal to x. I don't know what it is, but I'll do that. I'll change from Superman to Clark Kent. The base is 3. The exponent is x. This equals the argument. So, is there a common base I can get here? And the answer, at first might appear to look like there is not. However, 1 plays on anybody's team. How is that? Because 1 can be written as some real number, as long as it's not 0, to the 0 power. So 3 to the 0 actually equals 1. 1 could also be written as 5 to the 0, but we have 3 to the x on the left-hand side, so I'll do that. 3 to this equals 3 to that. Set the this equal to the that, and you get x is 0. Log base 3 of 1 is 0. 0 is our answer. Log base 5 of 1 is 0. The same thing's going to happen. Log base 13 of 1 is 0. So there is another property of logs that says, and you might have guessed this, log base b of 1 is 0. Let's continue. Okay, see if you can do problem 5 on your own. Okay, let's set this equal to x. I'm going to go ahead and change from Superman to Clark Kent. Who's in the basement? 9, the exponent, x. This equals the argument. This problem is a little more difficult to just kind of think 9 to what power gives you 1 over 27, and that's kind of what we have written here, so that's why this method will always work, the one I'm showing you. Is there a common base between 9 and 27? Yes, it's 3. So 9 is 3 squared, and 27 is 3 cubed. 3 squared raised to the x, you multiply those. I'm going to cross the line, change the sign there to a negative sign. Okay, so now we have 3 to this equals 3 to that power. I'm going to take the this and that, set them equal to each other. I'm going to divide by 2. And there is my answer. Log base 9 of 1 over 27 equals negative 3 halves. Negative 3 halves is the answer. Okay, the next problem. Log base 7 of 7 to the 32. You might be able to do this the quick way. 7 to what power gives you 7 to the 32? So you may be able to actually just write the problem down. Go ahead and do that problem. Okay, I'm going to set this thing equal to x. Go ahead and change this from Superman to Clark Kent. 7 is the base. The exponent is x. The argument is 7 to the 32. So 7 to this equals 7 to that. Set the this and that equal. You get x equals 32. The answer is 32. So we have another property of logs, and it might be worth remembering. If you have log base b of b to the x, you end up getting just x. Sometimes I'll call this the popping property, where that pops and you just end up with the x. It's kind of dumb to say it's the popping property, but that's maybe a way to remember this, that these letters here have to be the same. You know, like it was a 7 here and a 7 here. If this was 7 and this was 8, we wouldn't be able to do that. We'll see this property come up later on. Our next problem, this one might be a little too challenging to say, try to do this one on your own, problem number 7. I'm going to set it equal to x, and I'm actually going to make the statement that this equation here is an exponential equation. It's Clark Kent. What is the exponent? It has a log in it. That's the exponent. It's Clark Kent with a tattoo of Superman, whatever. I'm going to go ahead and change from exponential form to log form. So the exponent is log base 4 of 10. This equals, so that was the exponent. Changing it to log form, that equation, log, what's the base? Who's holding things up? The 4, and the argument is x. So log base 4 of 10 equals log base 4 of x. Log base 4 of this equals log base 4 of that. What can we say about this and that? Well, that this then equals that. And your answer then happens to be 10. And now that happened because this base here and this base were the same. In fact, there is a property of logs that says b raised to the log base b of x equals x. This is the second popping property. Those guys go away, pop, and you just get x. Let's put them side by side. There's the first popping property, where you log base b first of b to the x, and then this is the second one where you have b raised to log base b. Okay, those properties will be good to memorize. Let's go ahead and do the next problem. I want you to try this on your own, remembering what the ln is, what base that is. Okay, that ln means log base e of e to the 7th. So we could go, oh, look, this thing goes pop, and you end up getting 7 for your answer. Now, if you forgot that property, you could set this thing equal to x, change it to Clark Kent, and shortly you will see that x equals 7. So the answer here, any way you do it, using one of the properties or using just the definition, you'll get 7. Here is another problem. See if you can do problem number 9 on your own, remembering that the square root happens to be the 1/2 power, but there's a 3 there. Okay, so I'm going to rewrite this as log 10 to the 3/2 power, that square root. Put the 2 down there. By the way, the base of this logarithm is base 10. And just like the last problem, this thing goes pop, and your answer is 3/2. Could you set this thing equal to x, change it to Clark Kent, and get the same results? Yeah. Let's go ahead and do this problem right here. Log of 0.001. There's a few ways we can do this. The first way is set it equal to x and also realize that there's a base 10 there. Changing it to Clark Kent, I have 10, which is the base raised to the exponent, equals 0.001. Well, that 0.001 happens to be 1 over, there's actually 3 things after the decimal point, so there will be 3 zeros here. That's 1 over 1,000. The common base we can get is base 10. And so this is 10 to the 3rd. Cross the line, change the sign. This is 10 to the -3. X equals -3. So our answer is -3. We're done with this problem. Let me go ahead and do 10 again. You could have done this problem like this. You could have said this right here is 1 over 1,000. And you could have said, oh, 1,000 is 10 to the 3rd and moved it upstairs, so this becomes 10 to the -3. And then you could have said, pop, and you would end up getting -3 for your answer. Okay, so as long as you're following the rules of the properties, you should get the same answer. Let's go ahead and do a few more things here with logarithms. This one right here, wow. This is log base 7 e raised to the log base e of the square root of 7. Now I'm going to try to find the other one that we did. Oh yeah, it's this one right here. This property, hold this paper right here, where, is that the property I'm looking at? No, not the right one. That was nice. Here's the property right here. Okay, where you have b raised to the log base b of x, that goes pop, and you just get the x. So look what's going to happen here. You've got the same situation right here. You're just going to get the argument, which is root 7. Log base 7 of root 7. Now you can set it equal to x and do that, or you can realize that the square root is what power? The square root is the 1/2 power, and then that thing right there goes pop, and you end up getting 1/2 for your answer. Okay, this is a more complicated problem. We do the problems like this so that when you hit your homework, most of them are easier than this. Our last problem would be this one right here. I'm going to set it equal to x, and I'm going to change this to Clark Kent. 7 raised to the x equals 14. Is there a common base? Well, some of you might realize that 7 times 2 is 14, but that doesn't mean there's a common base. You can't write 14 as 7 to some power. This happens to be type 2 exponential equation, so we cannot do this yet. Okay, that's kind of a weak answer. That it is what it is. Taking a look at our picture there. Hopefully we've got good enough light. It is 5 o'clock, so the sun is going down, and the lights, I've tried doing this at nighttime, the lighting is not as good. Okay, when you have this right here, this logarithm, notice in your examples that b has always been a positive number. And this guy right here, a, is also positive. Now there's an exception here, like something else we cannot have. b cannot equal 1. Okay, so a has to be a positive number. That means it's greater than 0, and b has to be a positive number, which means it's greater than 0, and b cannot equal 1. Having said that, we'll come back to why that's the case. We're going to go ahead and do some problems that will help us with this here. The problems that we just did, let me see if I can find them. The ones where we're evaluating the logarithms, that should help you with 16 through 42 in your homework. So on these ones, it tells you to find the domain. Now what did we say about the argument? It has to be positive, which means this has to be greater than 0. Your book is going to ask you to do interval notation. So we'll put this in interval notation, parentheses, 0 to infinity. Okay, find the domain. So are they asking us to plug something into the function? No, they're just saying, what can this function eat? 0 to infinity. What can this function eat right here? Well, you take the argument, like we did there. There was the argument on the last one, and you have to say it's positive. It's greater than 0. So you solve this inequality. Negative 3x is greater than negative 10. And when you divide or multiply by a negative number on an inequality, it flips the inequality. So you end up getting x is less than 10/3. Nice planning on space here. Good job. Oh well, we made it. Look, there's all this space right here. I mean, what am I complaining about? So I'm going to write this in interval notation. The interval notation would be from negative infinity to 10/3 parenthesis. So some of you are thinking, hey, you can put a negative number into this? Yes, if you put x equals negative 1, you have a negative 1 times a negative 3, which gives you a positive 3. So you're taking the log base 2 of 10 plus 3, or 13. You just can't put a number like, 5 in there, because you'll have 10 minus 15 log base 2 of a negative 5. It just blows up. You don't want to do that. Now I put some problems here that were not logarithms so we can compare and contrast the domains. So our problems with domains are when you have square roots or fractions. Now we have logs to worry about, so I'm going to take the same argument when it's under a square root. That argument has to be greater than or equal to 0. Because you can take the square root of 0, you cannot take the log of 0. So see the subtle difference there, greater than or equal to? Greater than. So this one plays out the same way. You can solve that, and the answer on this one will be negative infinity to 10/3 bracket. You put 10/3 in there, you end up getting 10 minus 10, 0. You get the square root of 0. So here we have the 10 minus 3x. It's not the argument of a square root or the argument of a log. It is the denominator of a fraction. So 10 minus 3x cannot equal, I think you can tell me that, 0. So I solve this cannot equation. I don't think that's really called that. I'm going to divide by negative 3. And so x cannot equal 10/3. Now in interval notation, what that would look like is everything but 10/3. So negative infinity to 10/3, parentheses everywhere, union 10/3 to infinity. There's the answer. Okay. In terms of our logarithms, let's go ahead and finding the domain of a logarithm. We're going to go ahead and do the finale problem here, which is find the domain of this creature. It has all three problems: a square root, a log, and the bottom of a fraction. Now this one is rather challenging. Let's just go ahead and do this. There's three problems. You have the thing that's under the square root. The argument of the square root has to be greater than or equal to 0. You have the argument of the log has to be greater than 0. And you have the denominator of the fraction cannot equal 0. So this is just loaded with everything. I'm going to go ahead and solve this. Negative x greater than or equal to negative 10. Multiply by a negative 1 and I get x is less than or equal to 10. I'll circle that. This one I add 1, I get x is greater than 1. And on this one, this is going to actually be a little challenging because we haven't done log equations. 2 equals log base 2 of x minus 1. I'm going to change from Clark Kent. No, wait, that's Superman. Back to Clark Kent. The base is 2. The exponent is 2. This equals x minus 1. 4 equals x minus 1. X is on the right side. That equals 5. Now all this part where I put equals, I should have put what? Not equals. Not equals. There's the evil Superman and evil Clark Kent, and there it is. So let's put all this together on a number line. We have the numbers 1, 5, 10. So this guy right here, just use this right here, saying that x is less than or equal to 10. We're taking a common domain, by the way. And this guy right here says that x is greater than 1. And this guy right here says that x can be anything except 5. The question is, where do you see all three colors? You see them between 1 and 5. For some reason the camera turned off. if it turns off again, I'm going to have to throw a rock at it or something. That was not cool. Maybe it has a set time that it could record. Oh well. So back to this. I think before it turned off I was saying, where do you see all three colors? You see them between 1 and 5, but you don't see all three colors at 1. You actually do not see a red there. So I'm going to put an open circle there. And you don't see all three colors at 5 because green's not there. But you see all three colors between 5 and 10. Do we see all three colors at 10? The answer is yes. Green, red, orange. And so the domain, you don't see all three colors beyond 10. You only see orange is missing and red is missing to the left of 1. So our domain is, in interval notation, 1 to 5, parentheses on both of those, and then we go parenthesis 5 to 10, bracket. And there's our answer. That problem was rather traumatic. Do your homework and work on these. Okay, this is going to be on the harder side in terms of difficulty. So this will help you do 43 through 57. Let's go ahead and cover our last sort of topic with this, exponential and logarithmic functions. And the last topic happens to be something that looks like this. It tells you to find f inverse algebraically and geometrically. I'm going to go with the algebraically first. So how do I find f inverse algebraically? Well, change f of x to y. That was a 4-step program. Then I'm going to switch my x and y. And then step 3, solve for y. Well, it's hard to solve for y, but we can. Dun, 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 dun. That's the old Superman theme. I'll just keep going. I'm not going to go back and delete that. You're changing this from Clark Kent to Superman, so the exponent is y. The log has base 2, and the argument is x. Step 4 was replace the y with f inverse of x. Now my stomach is growling. Hopefully you're not hearing that on the video. Okay, so what are we going to do? Now we're going to find f inverse. We're going to do that graphically here. We're going to find the graph of that. Let's go ahead and put, there's the y-axis. Here's the x-axis. X, y. Well, I know how to find this guy right here. Y equals 2 to the x. It's the one where the airplane's taken off. And the thing to remember is it has a y-intercept of 1 and the point 1, 2. And it also has a horizontal asymptote. Here's the runway of, this is y equals 0. And we have the plane taken off, so we'll just kind of do a rough sketch here. Well, remember what happens when you find the inverse graph. Everything switches. So the y-intercept, which is 1, will now become the x-intercept of 1. Now, if you want to write that as a point, you have 0, 1 now becomes 1, 0. The point 1, 2 becomes the point 2, 1. The x-axis wall now becomes the y-axis wall. And now we try to mirror this through this line here, y equals x. I mean, it's not a very good drawing of that line. And when you try your best to do that, you end up getting a graph that looks like that. It's the logarithmic graph. All your log graphs will have vertical asymptotes of x equals 0. All your log graphs will have, the ones that have not been transformed will have an x-intercept of 1, and the point of b comma 1, and in this case it's 2 comma 1. So let's go ahead and summarize that. Here's the log graph. Now this summary, let's see if I can, man, there's a lot of pieces of paper here. This can't be good for the environment. I'd say no. Oh yeah, here it is. So we saw this a long time ago where we had the exponential graphs. There's two kinds of exponential graphs there, when b is greater than 1 and when b is between 0 and 1. Well, there's two kinds of log graphs where b is greater than 1, which is like the kind that we just did, and when b is between 0 and 1. And so those are what those log graphs look like. The crazy thing about these log graphs is they have this. This is the common thing. X is 0, the x-intercept of 1, 0, and it always has the point b comma 1. If you turn these to the side, the one where b is greater than 1 actually looks like the plane landing, which we're not used to when b is greater than 1 for exponential graphs. And then when b is between 0 and 1, it's the plane taking off. So let's go ahead and do our last problem and see if we can do a transformation of a log graph. So we're going to say, what is the mother graph? Let me go ahead and pause this right now and I'll come back. Okay. So looks like I'm going to have to merge 3 video clips together to get this long video clip. But in any case, I want to graph this graph here, which is g of x equals negative log base 3 of x plus 1. So the mother graph is f of x equals log base 3 of x. So the log graph is just something you have to remember. You have to remember that the mother graph has a vertical wall here, and that you can put 1 in there, log base 3 of 1. Remember, when there's a 1 there, that is 0. And then always has the other point, log base 3 of 3, log base 3 of 3 is 1, always has the point b comma 1 or 3 comma 1 in this example. So this graph looks like this. I'm going to try to make it a little lighter here. Oh well, maybe not. It looks like that. There's the log graph. So what we're going to do here is we're going to do transformations. And this transformation, I'm transforming this mother graph by going like this, minus f of x plus 1. And this is the part where everybody said, where did the log go? Remember, when you put x plus 1 into this function, it says log base 3 of x plus 1, which is what we have here, and we have the minus in front of there. Okay, so this graph is transformed, and doing the CBAD order, we go 1 to the left, and then this negative out here is a reflection across or through the x-axis. So my intermediate step, I'm going to go ahead and use red. So 1 to the left, this point right here goes 1 to the left. This guy right here goes 1 to the left. And the wall actually gets moved one to the left. So if we had to draw this, intermediate graph, it would look just like the blue graph, but getting shifted 1 to the left. Okay, the next thing that we're going to do is we're going to reflect this through the x-axis, and my final graph is going to be in black ink. The thing that gets reflected is this red point right here. So now we're looking at the red point. It gets reflected through the x-axis. I have that point right there. The one that's on the x-axis stays on the x-axis right there. And the reflection of this vertical asymptote through the x-axis, it stays the same. So now what we have here is we have a graph that looks like that and looks like this. So there it is, and you can see still when you turn it this way, it still reminds you of an exponential graph when you turn it 90 degrees. So that is the last problem that I have from 6.1. I'll go ahead and throw in one more problem, and it will be find the domain, because I know maybe I should have done one more problem like that. So find the domain of this guy right here. I'll call this, let's see, what were my domain problems? I'll call this number 6, and maybe I'll go ahead and place it in a different order when I post the notes. So this is f of x equals log of x squared minus 1 all over x squared minus 4. So how do we find the domain of this log function? We set the argument greater than 0. Now, because we've done graphs of logs, we can see why that's the case. Because the graph of logs, look at the domain. It's all x values greater than 0. So we're just going greater than 0. The reason I wanted to do this is if you had something in your homework like this, you would be able to do this. This right here is a rational inequality. The steps are put 0 on one side, we have that. Factor the top and bottom if you can, I can. X minus 1, difference of squares, x plus 1. All over, difference of squares on the bottom, x minus 2, x plus 2. This is greater than 0. We're going to call this function right here, let's just call it g of x. If I call it f of x, I'm going to get confused. And now I take the zeros from the top, which are -1 and 1, put them on a number line, take the zeros from the bottom and do the same thing. 0, 0, 0, 0. Don't forget, the ones from the bottom get no's. And hopefully you're reading down. No, no, because if you like to read up, you're like, on, what? So how many regions do we have to check? 1, 2, 3, 4, 5. But know this, and I said this in the other lecture, that these all have 1s. They're all linear factors. So your signs are going to alternate. So I'm going to go ahead and test a point right there. That's zeros in there. So I'll go g of 0. And I'm going to get minus, plus, minus, plus, which gives me, you put all those together, it gives you a plus. Now, you can alternate the signs if you want. There's minus and a plus and a minus and a plus. But if you have trust issues, go ahead and pick points from the other 4 regions, like, you know, maybe 5. And if you put 5 in here, look, plus, 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 which gives you a plus. if you put 1.5 in, 1.5 minus 1, this is plus, plus, minus, that's 1.5 minus 2, and then we have plus, which gives you the minus. Well, in any case, we are looking for when this thing is greater than 0, so we are going to consider the positive signs and not the zeros. And our domain for this creature here, log of that, and the base of that log is 10, would be from negative infinity to negative 2, union, what am I doing here? Okay, I gotta get the whiteout out. There we go. And, well, okay, so what I have here is, I put a bracket there, so I must be getting tired. Negative 1 to 1, union, 2 to infinity. That is the lecture. And just so you remember, I'm your teacher. Hey, good to see you guys. I'll see you on the next video.